There is no other way to put it, it's a graphical engine that renders column-free. I suppose we should start with why, right? Alright, first let's start with the point. And the point is pretty simple. This right here is fixed, this hexagon, in parts, because I haven't assembled it yet. The whole point is that the reason why we need taxi is because I would like to have some kind of debug output for fixed, to let me know when it errors, when it completes a task, when it throws a warning, etc, etc, etc. And what better way to do it than to have a massive column-free at the front with different emojis that will represent the success or utter failure of the program I'm running. I really need sleep at this point. Now, because I am who I am, I decided to do the simplest possible thing. Write my own graphical engine from scratch with no external libraries. And when I say no external libraries, I mean not even Vulkan. It is difficult and technical to describe why it's challenging or why it makes certain things easier, why certain things are more complicated, but let's be real, you're not here for that. You're here to see the silly face, aren't you? So you know what? Let's go to the explanation of how it works. So, let's start our problem with some kind of simple arbitrary shape. Or, you know what, let's complicate it a bit. And a bit more, just for the sake of the challenge. Now, if we select some kind of point on our board, how do we figure out if that point is inside our shape or on the outside? Well, we can do it using arrays. So basically, we emit some rays from our point going outwards. Now we check how many times our rays collide with our shape. And if they collide an even amount of times, that means the shape is outside. That's because if a ray enters a shape, it also has to exit. If they collide an odd amount of times, it means the shape is inside. I do believe if I just rotate this ray around, it is pretty easy to see why points on the inside would collide an odd number of times. But there is actually a way more important question to ask here. How would we compute this? How do we figure out how many times a ray has collided with the shape? As humans, it is tempting to think about it like so. Just emit a ray, keep going, and if eventually the position of a ray is equal to the position of a certain point on our shape, that means it collides, right? Well, yeah, that is true. In that case, that would collide, but a ray is a line, just like our shape, which means that it has an infinite amount of points. So in order to actually compute that, we would need to compare the positions of every single point on our ray to every single point in our shape. So basically, we need to compare the positions of an uncountably infinite amount of points with positions of another uncountably infinite amount of points. And that would take quite a long time, you know? This is the actual problem with this kind of visualization of these shapes. I am animating all of this in Blender, which is an extremely advanced software, so it's easy for Blender to create a ray and figure out if it collides with another object. But in actuality, the shape I've created is based on these points. And okay, I know it's a lot, but the point is, these are the points that Blender uses to draw the curve. What it does then is something called interpolation in order to connect them together. So these are the only point coordinates we know of. So how are we supposed to even figure out the coordinates of the other points along our shape? Well, once again, Blender can do it because Blender is advanced, but we're coding everything from scratch in C, so that, well, let's just say it complicates things. And so that's why we'd like to actually simplify our scenario a bit. Instead of a whole shape, let's just talk about a single line. A single straight line, just like so. Or, even to simplify it more, a single straight line segment, to be more exact. Now, if we select the point, how can we figure out if our ray will collide with this line segment? Well, this is still a tad bit unnecessarily complicated, so let's simplify it even further and let's say that we'd like our ray to be flat. Now figuring out if our ray will collide with the line is downright trivial. Basically, let's divide our playground into 5 segments. The one above, the one below, the one on the right, the left, and finally the middle. In this case, if our point is over the line or under the line, we know for a fact that our ray will not collide with the line. Same thing goes for when our point is on the left, there is no collision there. If our point is on the right, we finally get a guaranteed collision no matter what. But what about the middle? Well, in the middle, our ray can collide the line, but it doesn't have to. So how do we figure out when it collides with the line? Well, here's where we enter the neat part of computer science, because we've actually just entered the planning stage of the actual script, which means that this will just be mathematics. Now, I will put everything I say on screen as equations, but don't get spooked. They will be equivalent to what I'm saying. They're just there to solidify and specify what I'm talking about. So for example, if I say that we know a velocity of an object and we'd like to know how much it traveled in between our first time measurement and the second, then this is what it would look like as an equation. It may look complicated, but it is just equivalent to what I've said. I'm basically translating English into maths. And so with that in mind, let's get back to our line. First things first, let's formalize our line and define it as a function. A linear function, to be more exact, f of x is equal to ax plus b. So basically, right now we're effectively saying that our line is just a segment of a function, with the domain being from x coordinate of the first point to the second point. Why is that helpful? Well, it's helpful because if we ignore all the segments where we're certain and only focus on the one where we're not sure, in that case, in order to figure out, all we need to do is ask what is below our function and what is above. This is neat because now instead of an infinite amount of equations to compute, we can just compute one. All we need to do is check if our point's y-coordinate is above the linear function or below it. But even then, next question would be, what is that linear function? What is the a and b in this case? Well, since we do know the coordinates of the 2 points defining the line, we can just plug them in, solve it, and there we go. We've got the terms. This already allows us to render the area on the right of any line we want. There are some problems, of course, like what if it's flat or vertical or reversed, but all of these have some pretty boring solutions, so I'll just show off the code I was using at this point, and there we go. Neat. But that's just a line. What if we wanted to draw a whole shape? Something like a star. In that case, if we use the drawing method we've got so far, this is what we would get. Yup, it's quite bad, but I suppose it does make sense. We have been just checking if something is on the right of our line. We weren't really drawing a shape, so how do we fix it? Well, we don't actually need to fix it. That's because if you remember, the whole point of this wasn't to check if something is on the right of our shape, only how many times it collides. So right here, instead of coloring everything equally, depending on if it crossed the line, I'll just color it in brighter depending on how many times it crossed the line. Now you can see that some segments are in fact brighter than others, because they've crossed more lines. So, which ones do we care about? This kind of picture could be misleading, because it's hard to say, but the answer is we care only about the points that crossed our lines an odd amount of times, which right here I'll color in blue and the even ones in yellow. And there, we get a star. This is incredible. I mean, come on, that's such a clean implementation. Now, to be fair, it only works for straight lines, but still, quite impressive. Alright, from the post I did a while back, it is clear that we obviously can actually draw curves. So, how are we drawing these curves? Well, the trick is, we're not. Misdirection. Yes, these may look like curves, they may look like arcs, they may look like semicircles, but they're not. In reality, what they actually are is just straight lines. Because that's all our engine can handle. First, let's start with a circle. How can we define a circle? We can do it using a point that will function as its position and the value which will be the radius. There we go, a circle, courtesy of my old mate Euclid. Now we can make any kind of arbitrary circle. But what about an arc? In order to define an arc, we only need two more things: the angle of the arc and the phase by which it's offset. And using these 5 values, we can perfectly define an arc. Except define it how? Like, what is this arc? It's not a function because it loops on itself, so what is it? How are we supposed to model it? How are we supposed to use it in any way? Well, ideally, we'd like to model it using lines, because our engine can already render shapes with lines. So, let's add one more variable. That variable will be n. This variable will tell us how many points will make up our arc, and then we can just model it as a bunch of lines going in a circle. How many lines? n minus 1, because n is the points. And there we go! That's the arc. Now all we need is the positions of these points, and we're golden. So how do we get the positions based on our variables? Well, we have been dealing so far with our coordinates in the Cartesian system, so the position of each point on the x-axis plus the y. Damn, this is difficult to visualize. There is too much information. Hold on, let me just reset the camera and yeah, maybe just do it one at a time. This is quite confusing to describe, but if we briefly switch to polar, then it becomes downright trivial. We can just add the Cartesian coordinates of our middle point to the polar coordinates of our arc points, and there we go! That's the position. The polar coordinates we can get because the radius we have, and the angle is just the face, plus the distance along our angle. So the angle is multiplied by the index of our point, divided by the amount of points, and normalized to get a nice and consistent value. Then we just take this radius angle, we convert it to Cartesian, and voila! It is finished! We can draw an arc! Or rather, we have a function that creates an arc, because to actually draw an arc you need two arcs, like one like this and one like this, and then there, this is how our engine will draw it. Simple! This is how I've drawn taxi, by the way, this taxi right here from the post. The way I drew it is obviously the first arc, then the second smaller arc, flipped, that for the shape of the mouth, and then for the eye is just a single arc. But the way our engine draws it is, it always connects the last point of our shape to the first point of our shape to, enclose it. And so that's why if you just draw an arc, you get a semicircle. The point is, it works! Kind of. Okay, no, the engine works. Like, there are sometimes some lines that are just there for some reason, some artifacts, but the engine works. The problem being, it works really, really slowly. It takes exactly 180 milliseconds to render that image, which may not seem like a lot, until you realize that that effectively means 8 frames per second. Especially considering that I am running this code on my computer, albeit on a WSL, but still on my big beefy machine. If I am to actually take this code and put it on a Raspberry Pi 5, it's going to be significantly slower, so we need a lot more time. Or rather, a lot less. You get what I mean, why am I explaining this? Now, the reason why it takes so long isn't really a surprise. So far, we have this equation right here to check if a pixel is going through the line. Now, this equation we have to calculate. But how many times? Well, we calculate it for each and every single line. So, we effectively calculated n, where n is our number of lines, times the width of our image, which is 400, times the height of our image, which is 300, because that's the amount of pixels. So it's effectively the amount of pixels times the amount of lines. And this number is pretty high. It's not crazy high by computer standards, but it's pretty high considering that this is meant to be in real-time engine. How can we make this better? Well, there are obviously two ways. We are calculating this equation this many times, so there are two things we can do. We can either A, calculate it less times somehow, or B, we can calculate it in a smarter way. We're gonna start with the classic, the easier option, which is just decreasing the amount of calculations required. How can we do that? This is kind of simple because for a shape we can just draw a rectangle around it, and we know that anything above or below or to the left or to the right of that rectangle is irrelevant. It doesn't cross our shape in any way, so we can just ignore it. And there we have already very significantly cut the amount of calculations required. But that was the simple fix. This speeds up our engine around twofold, which isn't bad, but there is so much more we can do. How? Well, allow me to introduce you to the concept of parallelization. So far, we've effectively been checking this on a pixel by pixel basis. But what if instead we checked it for multiple pixels at once? Well, then we could draw it in segments, and that is what threading is for. Basically, so far, if we have a render, this is how we do it. Simple, obvious, and exhaustingly slow. But if we'd like it to go faster, then we can just start a couple of threads and have each of these threads render a part of the image, resulting in a 5-fold speed up. This is where the bulk of the optimization came from, these couple of lines right here. I would love to say it was difficult, but to be honest, it was just C. Like, it worked on the first try. Actually, explaining how it works would require me to make a whole separate video on function points or just pointers in general. And I still think it's extremely interesting, but it would be really computer science. 5-fold increase. Yes, we have actually sped up our engine from 150 milliseconds to around 10. This means us speeding it up from 8 frames per second to around 100, without cutting anything, without reducing quality in any way, just sheer optimization. In order to truly explain it, it would take a little bit more background, because I would need to once again explain pointers, which I have explained in the past, but this time I would need to introduce the concept of function pointers, explain how functions are values, then explain what I'm doing here in order to generalize input into a void pointer, blah blah blah. The point is, it is really interesting, but it would require a whole separate video. And right now, we just simply do not have the time for that. But to recap, what we have achieved so far is a real-time engine which can actually render column 3 in real time using only the CPU. Alan Turing would have been proud. Okay, I kind of sped through the optimization segment because there are a lot more things I could have mentioned there, but they're all kind of technical, and I do understand that unless you are specifically a C programmer, that wouldn't be interesting for you. But so now let's just talk about the next thing, which is utilities. That's because whilst the engine works, that doesn't mean it's exactly usable. And so these will include some more boring things, some of them will be more interesting. Like for example, right now, so far, in order to draw any shape, you first need to create the shape, you need to set its size to be 0, then you need to add the points, then you need to draw the shape, then you need to delete the shape. Which is a bit of a hassle, because you do actually need to keep track of every step along the process. It's a bit annoying, and just with a snap of my finger, there we go. Now you don't have to do all that. You can just create the shape, do whatever you want with it, that's it. The engine takes care of the rest. A little bit of magic, which I would love to explain, but once again, I am painfully aware how much no one cares. It's annoying that I need to skip over all of the cool things just because society doesn't accept low-level programming. And before you complain that this is not low-level programming, it's obviously relative. But considering how the majority, vast majority of programmers either do things in Python or even worse, God forbid, are actually just front-end developers in TypeScript, I feel quite comfortable calling C low-level, alright? Another utility thing would be the colors, because as you might have noticed, so far I am only drawing in red. What's up with that? Well, what's up with that is that to file I actually were writing characters. Even funnier, since I was writing characters and I was using them as Boolean values, I was mostly writing 0s and 1s, and I did add the new lines, which means you could have just opened the text file and seen taxi there, which I think is pretty funny. This effectively gave me the option of 256 different colors I could have chosen. So far it hasn't been a problem, but at this point it became a problem, and I'll get soon to why. Basically, up to this point I was just manually adding the colors I wanted, because, well, 256 options is quite a lot when you realize that you get to choose which colors you add, and then just adding them and, coloring things to my will. But this is not great long term, because what if we need more than 256 colors? This required a slightly inconvenient fix, not for the reasons you might think, and that is switching from 256 different colors to red, green, blue, alpha, which means switching from 1 byte of information per pixel to 4 bytes. The reason why it's so annoying is because in C you have manual memory allocation, which means you as a programmer need to manually tell the program how much memory to allocate. And the reason why it was so annoying for this particular change is because, for example, if I create a buffer for all of the pixels, I need to tell C, hey, I'm going to need 400 times 300 times 1 bytes long buffer. Why this many? Because 400 is the width, 300 is the height, and 1 is the amount of information per pixel, so this many bytes. If, however, I want RGBA, then each pixel will require 4 bytes, not 1, and so we'll actually need 400 times 300 times 4. This on its own may not seem like a big change, until you realize that up to this point I was skipping the multiplication by 1 because it wasn't doing anything. Which means that in order to actually implement this, I had to go through the entire code and find every single place that needed to be multiplied by 4 in order to engine to work. And this is even worse than it sounds. That's because when you are struggling with memory allocation, and when memory allocation fails, you don't get an error. No, you get a seg fault. You see, we live in the future, so in almost every programming language, if you make some kind of error, the program will tell you exactly where you made that error, what is the error, and really often also how to fix it. Ta-da, convenient. Programming is really easy. That's why errors are great. We all love errors. What we don't love is the program breaking without errors, which is what happens when you mismanage memory. So basically, if I allocate a small buffer, but write to it a lot of data, the buffer is going to overflow. And in that case, that's just going to break everything. Because operating systems and really often hardware have securities against this sort of thing, it doesn't actually crash your computer, thankfully, but it still leads to a seg fault, which means the program isn't running. And what's really annoying is that whilst this is what you would get with an error whilst trying to compile, this is what you get with a seg fault. No information at all. Figure it out yourself. It's your mess, you have to clean it up. And actually, this is where the video originally was meant to transition to hardware. So this, taking my graphical engine and then implementing the screen. But the video is already too long, let's be real. So instead, I'm going to end it in a different way. And you better hold your horses because it's going to be interesting. That's because I had a very specific reason for adding the utilities to my graphical engine. I don't need them. I can very happily make things without the utilities. I have done that for years. However, at this stage of the graphical engine, before I added the utilities, before I added the optimizations, before I even added the color option, Patsy decided to take a shot at this and ask me for the code, which is why I created the GitHub repo. And after they got the code, the next day they returned with this. I don't think you understand just how unusable the engine was at that point. This is with no previews, this is with nothing convenient about it, this is just a raw code and point positions, alright? And so this gave me an idea. The code right now is open source, and on my second channel, where I'm streaming the creation of fixes in general, I'm going to make a tutorial video on how to run it. And here's where you come in. That's because when it comes to stuff like quantum mechanics, I've pretty much gotten the explanations nailed down. I do analogies and it works out. When it comes to chemistry, it doesn't matter how theoretical it gets, I can still do some kind of reactions to show off what I'm talking about. But when it comes to computer science, it's tricky. I can visualize the mathematics just fine, but I think it's so much better to play around with them. There's just so much value lost in just watching a video about it. And so that's why the code is open source. And I would really encourage you to go and play around with it. And I don't just mean draw the shapes. Like, yeah, it's a good start, but I would really recommend trying shit out, trying things out, going into the engine code, trying to change some things, trying to read it. It's not the most readable code in existence, but by my standards, it is extremely clean. So, I hope you enjoyed this video. I hope you will give Taxi a shot, and I hope that you've learned something. Because goodness gracious me, have I spent a lot of time just losing my mind over code. Anyway, I would like to thank my patrons, Tefta, Quaza, Acronymus, Macaroni, and Black Thunder for helping me keep the lights on, helping me keep the food warm, or getting any kind of food at all, because let me tell you, YouTube ad revenue does not pay well when you're a small YouTuber. I really do appreciate your support. Without your support, I wouldn't be able to work on Fix It at all. I wouldn't be able to get the live streams on this channel to become a little bit more high budget, and I wouldn't be able to work on another super secret project I have ready for, well, it's not really fair to say Stream 1000 because it kind of goes beyond that. Patreon only secret, you'll never know. I have a Discord server, collecting money for charity, second channel, all that stuff. And for now, that'll be it. Thank you very much for watching and have a great day. Bye!